Sure to have today Francesco with us. Well, Francesco, La Barbera, he's getting more often coming to the IC to work with us, so you will probably see him more often. In any case, he made his PhD with Capaccioli in Napoli. Then soon afterwards he got the permanent position. By the way, he is the youngest Italian, I guess that's astronomer, no?
Yeah.
Yeah, okay. Got the permanent position, you know, at which age, by the way?
27.
27, so it's amazing. So it's, yeah, and he's there in the Observatory Capo dei Monti in Napoli, and well, his interest is he's been working he's interested in several, always related to galaxy evolution, of course, and the environment, for example, is something that he contributed quite a lot, and also the gradients are well beyond the effective radius, 8 or so effective radius with photometry. And in the last years, we've been much more interested in the IMF studies. You remember just last Friday, Nacho thesis on the IMF stuff on early type galaxies, and part of that work has been done in collaboration with Francesco. So, okay, so Francesco is.
Okay. So, good morning, everybody. I'm very happy to be here today, and first of all, I would like to thank Jesus and Alejandro for inviting me to give this talk here today. So, I'm going to talk to you about our work in the last few years about the non-universal initial mass function of early type galaxies. So the stellar IMF is essentially the mass distribution of stars collectively born in one event of star formation. So you can find, you know, some nice review in Krupa 2012 about many issues related to the definition of the IMF itself. So why is it important? Why do we care about it? Well, for several reasons, actually. It governs the matter cycle of galaxies through the transformation of gas into stars. It sets the mass scale of galaxies through the mass-to-light ratio. It is deeply connected to the physics of star formation, stellar evolution and structure. It also drives the chemical enrichment of the interstellar medium in a galaxy. And of course, it enters the conversion of several diagnostics of star formation. So it's a quite important ingredient of astrophysics in general. So what do we know about the stellar IMF nearby? So in star clusters and OB association for the Milky Way and Large Magellanic Cloud, where we can actually resolve the stars and then count the stars to derive the slope of the IMF as a function of the mass of the stars itself. So this is from a Krupa 2012 review. For different stellar systems, slope as a function of the central mass of the stars. So essentially at masses above solar, you have a slope which is consistent with salpeter slope, which is in this notation 2.35, which is around here. And then at lower masses, you get a flattening, which is essentially the Krupa or Chabrier IMF with a shallower slope. Of course, this kind of plot is by construction, let's say, biased to metallicities which are, let's say, below around solar, and also to densities which are in this regime, which is essentially the kind of stellar systems that we can observe nearby. So when we go to more distant systems, we cannot actually count the single stars, so we cannot derive, you know, in the IMF slope in this direct way. And we need, first of all, we need to adopt a parametrization for the IMF. So there are different ways to do this. One way is to adopt a single segment power law IMF, which is, let's say, generalizing the salpeter 55 IMF. This is the expression. So with this notation, the salpeter slope is 1.35, and so this is essentially the orange curve that you can see in this plot here, plotting, let's say, number of stars as a function of the mass of the stars. So the group IMF, as I was saying, we know that it's flatter, let's say, lower masses, essentially in this range. So a way to generalize this, for instance, is to introduce a bimodal low-mass tapered IMF that was done in Vazdekis et al. 96, where essentially you keep the low-mass end of the IMF flatter, but you can still change, of course, the slope of the distribution itself. So changing the slope, essentially increasing, making this function steeper, you increase the fraction of low to high mass stars in the IMF in both cases, either unimodal or bimodal. Of course, in the case of the bimodal distribution, you keep the low mass end flatter, which means that you don't have as many as very low mass stars as in the unimodal model. So I want to be really, I want to emphasize, this as much as possible, that there is no real a theoretical or also an observational motivations for either of the two distributions. But in practice, since you need a parameterization, I mean, this is a very, this way of proceeding is very practical one to change the dwarf to giant stars ratio in a stellar population. Okay, so now I will just show you a few slides about gravity-sensitive features, in case you just didn't hear enough about that from last week. And then I will show you the results that we have been accumulating, in the last few years. So, well, the idea is, in principle, is a simple one. So you have, let's say, some features in a stellar spectrum, like, for instance, this is the sodium 8200, or this is the Wings 4 band, which are very prominent in the spectra of dwarf stars, which are in red here, and are barely seen in giant stars, which are, let's say, green and black spectra here and here. And of course, you also have the opposite case, like, for instance, the calcium triplet, where you can see that the feature is prominent, let's say, in the spectra of giants, while it is barely seen in the spectra of dwarf stars. So because of that, if you look at these features, for instance, in the unresolved spectrum of a galaxy, you can compare, let's say, that spectrum with the prediction from a Krupa-like stellar population models. If there is an excess of absorption, you might infer, let's say, an excess of low-mass stars in the IMF. So, as I said, in principle, it is simple. It is an old idea, let's say, since the 70s or even before. But the first studies, of course, were quite inconclusive. And the main reason is that, as you can see here, this is a few percent effect. I mean, the deviation, let's say, between a Krupa-like model and a more bottom-heavy dwarf-enhanced model is just a few percent level in regions which are usually affected by many different issues, as I will show you. So the first studies were quite inconclusive. Then the issue was raised again in Senaro et al. 2003 by looking at the calcium triplet. At that time, there were, let's say, no way to have, let's say, stellar population models with varying abundance ratio. So the result was hampered, by the sensitivity of this specific feature to calcium abundance. So we have to give credit to Van Dokkum and Corroy in 2010 to have raised again the issue more recently then, and also comparing to stellar population models with varying abundance ratio. So in their approach, they adopted the spectral fitting, first for stacked spectra in Virgo and cluster early type coma cluster early type galaxies, then for a bunch of galaxies in the Sauron sample. In this spectral fitting approach, they compare to theoretical stellar population models with varying abundance ratios. These are all the parameters they change, when playing with the spectral fitting. So it's 21 free fitting parameters, including the slopes of the IMF in different, mass regimes. And they claimed that actually there is a significant IMF variation among galaxies. These are the most massive guys. This is velocity dispersion. And this is the IMF. This time, what they show is the excess of the mass to light ratio in the IMF with respect to what you would get for a Krupa-like distribution. Of course, more dwarf stars you have in the IMF, more the stellar mass to light ratio is. And as a consequence, you get higher along this axis. Okay, so this is a way to show essentially that you have an excess of low mass stars in here. So, okay, before I go ahead, I would like to emphasize, and this is, I think, something that I couldn't have emphasized enough, that this is an incredibly tough problem, extremely tough problem. As I was mentioning before, you have, in some cases, you have to appreciate, let's say, a few % variation, for instance, in this sodium 8200 feature, in a region of sky where you have telluric absorption, let's say, at the level of 80%. So on top of that, if this were not enough, you have, of course, uncertainties in your stellar population models. This is a comparison of the Padova and Atmov isochrones for the same chemical composition and same age. And you can clearly see that there are differences in the isochrones at the level of 100K or even more, both for giants and dwarf stars, dwarf and giants. And the bad thing is that at least for some feature, for instance, this is the TiO2 feature, which is quite sensitive to the temperature of giants. The effect of varying, for instance, the temperature of giants by, in this case, by 200K is quite degenerate with the bottom-heavy IMF, which is the red spectrum here, while the black spectrum is the Krupa-like case. So if you are not, depressed enough, let's say, by these issues, there is also the degeneracy with abundance ratios. So in the case, as I was mentioning, for the scenario at all work, so in some cases you can have a similar effect of a bottom-heavy IMF, which is the red spectrum here, compared to a Krupa-like black spectrum. When you then change the abundance ratio, in this case you have a denounced calcium over Phi abundance. You can see that red and blue are pretty much the same. Of course, there are some good news, and this is essentially the reason why I'm here today. So, first of all, we are now at the point that I think in terms of instrumentation and also data reduction quality that we can manage, with these kind of issues quite well, as I will show you. And the good things here, that this kind of degeneracies can actually be, you can break out these degeneracies when you compare features which are at different wavelengths, let's say from the optical to near infrared. In this case, you break the degeneracy between stellar population parameters, let's say like the temperature, for instance, or more seriously the abundance ratios and the IMF itself. So, say that I will try to summarize, let's say, the results that we have been obtaining in the past few years about the IMF as a function of galaxy mass, cluster-centric distance, time, and also something about the galaxy environment. And then I will talk you a bit more extensively about our recent works based on the XSHOOTER spectroscopy for nearby early-type galaxies. So, this is more or less the list of people which have been involved. Mostly it's me, Ignacio, and Alejandro, and a wide list of people that you see here. Some of them participating, let's say, to specific aspects of this project. And I really want to emphasize, the great work done by Nacho, Martin Navarro, and the important contribution that he gave, in the last 2 years for this kind of project. So, as you hear last week, by the way. So, everything started from the Sloan. This is in our first 2 papers about that, Ferreras et al. 2013 and Barbera et al. 2013. So, we selected a sample of bright early-type galaxies from the Spider sample, which is a carefully selected sample of early-type galaxies from the Sloan. So, these are galaxies nearby in a range of velocity dispersion with a low level of internal extinction, so you don't have to worry too much about dust. And we built up a set of 18 median stacked spectra with very high signal-to-noise ratio and in a range of velocity dispersion from 100 to 320, about 300 kilometers per second. So we compared the properties of these spectra to comparison of the Miles extended MuSCAT SSP models from Alejandro with varying age metallicity and IMF, taking also abundance ratios into account. So this has been, as a matter of fact, this has been after the work of Conroy and Van Dokkum, let's say the first work where the IMF-sigma relation has been derived for the whole population in a global way for early-type galaxies. So, okay, in the analysis we selected a number of features, the Balmer lines, which are mostly age indicators, the total metallicity indicator magnesium iron prime, then a variety of IMF sensitive features from the optical to the near infrared, and then some other features which are actually sensitive to the abundance ratios in order to break the degeneracy, as I was mentioning before. So, in order to account for theoretical models, you can essentially follow the approach of, which is the one possibility, the approach of Corot and Mandocum, rely on theoretical stellar population models. So, in this case, you have to rely and trust the theoretical calculations, you know, about all of that. Or, I mean, what we decided to do here, in order to, let's say, have some sort of independent approach, is to use the data themselves in order to account for the abundance ratios. And the way you do that, essentially, you have a fixed color here. You plot your IMF sensitivity indicator as a function of the magnesium over iron, or whatever, let's say, abundance indicator that you can have from your spectra. This is data. There is no modeling here. And you model essentially this with a fitting, for instance, with a line fitting, these trends. And then, I mean, this kind of lines, they tell you how you have to correct your galaxy, whatever its abundance ratio is, to solar scale. After this correction is applied, you compare to solar scale models. So everything is consistent. And this is data. I want to emphasize this more and more. I mean, you're not relying on theoretical or even models, whatever kind of models in this case. The difference is essentially the sensitivity of the features. It's just to emphasize the different sensitivity. These are IMF indicators. These are mostly sensitive to the abundances in blue. And the purple ones, or whatever color is this one, let's say, is sensitivity to age and metallicity. So we have, let's say, very selective features in order to disentangle different effects. So, okay, and here, besides, you know, the fact that you can use these trends for correcting the effect of abundance ratios, the good thing here, and you can start seeing that already, you know, in these plots, that you have a significant variation of IMF sensitive features along these axes, okay, with velocity dispersion from 100 in blue to 300 kilometers per second, okay? While in essence, if you move at higher abundance ratios, you see that the range is pretty much the same, or eventually lower in some cases. So it's already very clear from this plot that the main effect on gravity-sensitive features is that of galaxy velocity dispersion and not abundance ratios. Okay, but then you can go, of course, further. Then you know how to correct your features to solar scale. Tell me. Yes, features which are sensitive to the gravity of the stars. Yeah. So you go further. You know how to apply the abundance corrections, and then you can correct your indices to solar scale, and you can compare with the solar scale model predictions. So we adopted a best fitting approach, fitting all features simultaneously. So you can see the stacked spectrum. Stacked spectra is circles with error bars in all these panels. So each panel is plotting an IMF sensitive feature as a function of the total metallicity indicator magnesium iron prime. And you can see essentially that as a result of this fitting procedure, you can describe all features simultaneously with a sequence of increasing metallicity, which is here. It's a metallicity varying, for instance, from minus 0.2 to plus 0.2. A sequence in age, which is the difference between the black and the orange grids, and also a sequence of increasing IMF that you see in these along these axes on the grids. The grids are simple stellar population model predictions, but of course we went farther than these, and we also considered more complex star formation histories, like for instance 2 SSP models and also 2 SSP plus abundance ratio models. So, okay, so you can fit all features simultaneously. This is the previous one was for unimodal models. For bimodal models, it's pretty much the same. So you cannot really disentangle based on these features. And at the same time, of course, we also fitted the Balmer lines and the magnesium iron prime. So you get a very consistent, fitting among all selected indicators that you have defined. And this is essentially the IMF trend that you infer from that. So you have an increase of IMF slope, okay? This is for unimodal and bimodal models as a function of velocity dispersion. This is galaxies with, let's say, Milky Way-like IMF, which are here. For instance, this is the group IMF, okay, at low velocity dispersion, and then it keeps going on up to high velocity dispersion galaxies where you have a more bottom heavy, so a higher slope IMF. You can clearly see, I mean, this is also something that I want to emphasize. The slope of this relation depends actually on the kind of modeling that you are using. For instance, if you use 2SSPs plus some residual effect of the abundances that you can include in the modeling, depending on the indicators that you are using, as it was shown in Ferreras et al. 2012 and 13. But actually, the main point, and this is the really important point here, is that there is essentially no way to remove, at least, I mean, with the variety of methods that we are applying, to remove this trend. This trend is very robust, it's in place, and it has been also found by other studies, like the nice work done by Chiara in 2014 and 2015 one. So at the moment, there is no other way to fit all these features simultaneously without invoking an IMF variation with sigma. Okay. So we went further, you know, following the idea of stacking the spectra as a function of different quantities, and it was this was in our more recent paper in 2015, beginning of this year. So as I was mentioning before, you don't see much variation of the IMF sensitive feature as a function of magnesium over iron abundance ratios at fixed velocity dispersion. You can go further at this point, you can stack your spectra as a function of both quantities independently, as a function of sigma or magnesium over iron, and this is what you find essentially. You have this, the nice trend with the sigma, not a big surprise, but then at fixed sigma, which is a fixed color here, you don't have much variation of IMF slope with magnesium over iron. So the real quantity which is important here is sigma. So you should consider that this is not a trivial statement in a way, because it was, for instance, claimed by Corroy and Madocum in their 2012 paper, when plotting gamma either as a function of sigma or magnesium over iron, that it is this latter quantity that drives the trend. But actually, when you have many spectra, you can stack according to both quantities individually, you can see that it's sigma the main driver. And by the way, this is also more consistent to what you see from dynamical constraints to the IMF. Okay, I want to move further with another parameter, which is essentially metallicity. So this is the work with Nacho, the very nice work based on the CALIFA team, of course. We selected a sample of 24 L-type galaxies from CALIFA nearby, and this time we were able to to derive the IMF slope locally. So we're not talking now about the integrated properties over the Sloan fiber, but we are talking now about the local properties at a given position in a galaxy. Okay, so you can derive your local gamma, your local IMF slope, and plot it as a function of velocity dispersion. This is a local velocity dispersion, it's not an integrated one. And in this case, you don't get much of a correlation, actually. There is a correlation, but it's not so tight, indeed. And the same happens when you plot with magnesium over iron. As you can see, there is not much trend, which is also consistent with what we saw from the Sloan spectra. And this is what you get when you plot as a function of total metallicity. You get a very nice correlation. Of course, there is still some scatter, but there is a nice correlation with total metallicity and the IMF slope. This applies, of course, to this sample of CALIFA galaxies for the indicators that we have selected in this case. These are mostly galaxies with velocity dispersion above 200 km per second. So we should have this very clearly in mind, that we should think that a relation like this applies to every kind of structure in the universe. Even because, for instance, in the Milky Way, we have a huge variation of metallicity, but still we don't see, for instance, the bottom-heavy IMF. And this is also something also that I would like to emphasize. The fact that there is this correlation, it doesn't mean that metallicity is driving physically the slope, but it means that there is a relation between the two, in the sense that, for instance, I mean, whatever is driving, let's say, the chemical enrichment of a massive L-type galaxies is also determining, let's say, its dwarf to giant ratio in the IMF. Okay, we went further, always talking about the local properties, and you can... Yeah, you get a correlation in that case because of the tie correlation, let's say, between the average velocity dispersion and the average metallicity. So if you, let's say, integrate this local relation, considering the correlation between metallicity and sigma, you expect to have a correlation with the average sigma, which is pretty much consistent with what you see in SLOAN. So this is also explaining, in a way, the global relation that we get from the SLOAN. Okay, so you may ask yourself, but maybe it's already somehow, included in the previous plot, where this dwarf-enhanced population is actually found. I mean, the spatial distribution of this population inside a galaxy. So as a function of the galactocentric distance in an early type galaxies. And these are the two works, once again, with Nacho. Thank Nacho for that. So this is, we got very nice data with OSIRIS at the GTC and combined that with optical data from WHT with also Nacho Trujillo. And we derived the IMF slope as a function of galactocentric distance for a typical massive early type galaxies, which is orange here, and the typical, let's say, low velocity dispersion early type galaxies, which is the blue one here. You can clearly see in the first case you have a very nice IMF slope gradient from bottom heavy here in the very core region to, let's say, more Krupa-like in the outer part, while essentially for the low velocity dispersion galaxies you don't see any gradient whatsoever. So you conclude that at least for some massive early type galaxies you have gradient and the dwarf enhanced population is in the center. But then, I mean, you immediately realize that this is not for all systems, probably, or at least there are cases for which this is not true. This is the study where we analyzed 1277, which is probably a unique case of a massive rarely compact galaxies in the nearby universe. So we derived the IMF slope as a function of galactocentric distance with a variety of indicators. And you see that in this case, you don't see much of a variation. So the IMF seems to remain bottom heavy also at a quite large radii. So this, if you put this picture together, I thought we're talking about 3 galaxies, but let's say this could favor, let's say, a 2-phase formation scenario where you have a compact core with a bottom heavy IMF at high redshift, and then you keep accreting outwards a more Krupa-like, let's say, stellar material from lower mass systems. Okay, and just to mention here the work done with the Shards collaboration for the IMF at the Z1 with always with Nacho. Okay, so now some issue related to a bottom heavy IMF, something that is at the same time simple, but maybe it's not emphasized enough, I think. So if you have a bottom heavy IMF in a massive early type galaxy at all time, you're essentially saying that you never had so many giant stars in the population of stars you have in that system. So you're not enriching much the interstellar system, and then it's very hard to get high metallicities in massive galaxies, which is actually what you see in the nearby universe. So this is the toy models, the chemical enrichment toy models done with Carsten Weidner, who was before here at ISC, and then Ferreras more recently in 2015. And you can see that for a pure time-independent bottom-heavy model, you have essentially metallicities in the stars of the galaxies and of this model, at least, that are always below -1, while the typical metallicity of a massive galaxy is certainly above solar or around solar, let's say. So the only way to reconcile, let's say, the finding from the IMF sensitive features and the bottom heavy IMF in massive galaxies is to invoke a time-dependent scenario where you have, let's say, a top heavy phase at the beginning, where let's say you had a very strong star burst in the system, and then at some point, I mean, you have so much energy that you are injecting in the medium is promoting, let's say, fragmentation at low mass, in the low mass scale, and then you switch into a bottom heavy phase. So there is no physical model for that at the moment. This is essentially an assumption, but it seems to work in the sense that you can reconcile a number of constraints that you have from the observations, including total metallicity of the massive galaxies, and also the fraction of low mass stars that you have in the IMF as inferred from our studies. So in the work of Ferreras et al. 2015, we made, we found that whatever you change in the way you parameterize the IMF, if the IMF is time independent, you can never match all the constraints simultaneously. So no matter about the Lomasan cut, the characteristic mass, or the slope of the IMF, but you have to invoke a time-dependent scenario. So it seems to be really necessary. So something ongoing about the environment, you can think to split galaxies according to the environment where they reside, and this is done with Luma spectra. This is splitting galaxies according to field and groups. And then you can plot your IMF sensitive features as a function of velocity dispersion, and you find that the correlation with sigma is pretty much the same. So it seems that this is really an intrinsic property of the galaxy, as you were also expecting from the time-dependent scenario, and it's not much influenced from you have, let's say, around there. Okay, now I would like to spend a bit more, let's say, about our XSHOOTER work, which is the most recent one, actually. So if you are still skeptical about the IMF variations in early type galaxies, then maybe you'll be convinced from that. This is essentially we try to gather the best possible spectra that we can get from nearby early type galaxies at the moment. So for this reason, we went to the VLT with XSHOOTER. And we took very long integrations for two typical early type galaxies with a velocity dispersion of 300 km per second nearby. So I want to emphasize, even in this case, that reducing this data is insanely complicated because you have to reduce and combine more than 40 highly distorted echelon orders. So this is really not trivial, but in the end, it pays back, as you will see. So the amazing properties of the instrument is that essentially in this way you can get spectra from 3000 angstrom through the K band. So you essentially get everything you may like about your spectrum, with a resolution which is on average around 6000 for the kind of setup we adopted. So, and we spent around 5 hours per target. So we have spectra with amazingly high signal-to-noise ratio. So these are our targets. Essentially, both of them have a typical velocity dispersion more than 300 km per second. The main difference is their abundance ratio, which encompasses the range which is typical for high velocity dispersion guys. And they are typical ellipticals in all regards, well fitted by the Vauclair model. Okay, these are the 6 radially binary spectra that we got in this case from the very central spectrum outwards, out to one effective radius. There is no smoothing. These are the spectra as they come up by radially binning the data. So you have a signal-to-noise ratio per angstrom, which is above 400 in the core of the galaxy, and still it is above 100 in the outest bin, all over, here from 3000 to 2400 nanometers. So this is amazing. As far as I know, this is the best kind of spectra you have for nearby early-type galaxies in terms of spatial and spectral resolution, integration time, and so on so far. So what we did was, in this first work, was to combine the optical features, which are here, with the near-infrared wing-for band feature, and constrain the IMF simultaneously using the information from all these data. Okay, something that we did very carefully, since we have this amazing data, was to check for possible systematics, like, for instance, the telluric contamination in the data. And just to make a long story short, this is, for instance, the result of one exposure. This is one exposure of our data, and this is the way we can model the telluric lines using 2 independent approaches, either using telluric standard stars or Molech fit. You can see how both cases you match very well the data, which are in black. Actually, you can barely see them, and you get something which is, by comparing the different approaches, you can really say that you can correct your sky contamination at the level of at sub% level, which is 1 order of magnitude below, the signal that you want to appreciate. So, and this is done essentially because of the high signal-to-noise ratio and also the amazing resolution for which you can essentially see each telluric lines one by one in the spectrum. Okay, then you can go further with stellar population analysis for this first galaxy G1. So this is the age and metallicity as a function of galactocentric distance. The metallicity profile is quite typical for this system with a smooth gradient with lower metallicity outwards. And this is the age profile combined using many different approaches to constrain the age, actually. In the very core region, because of the extremely high signal to noise ratio, you can also use the age gamma sigma indicator, which is a pure age indicator insensitive to the age metallicity degeneracy. In general, what you see from this kind of plot is there is no much age gradient in the galaxy, whatever approach you use, although, of course, there is some systematic offset among different approaches, which is the usually well-known absolute age scale calibration for all stellar populations. Say it again, top age? No, no. In principle, you could have ages up to 17 giga-years. This is using the Padova models. So this is just what you get from, from different approaches. And this is for, you can also model the abundance ratios, because for this kind of spectra, you have everything. So you also have the optical indicators, whatever you want is there, actually. So this is alpha over iron as a function of galactocentric distance here. Still, we use a different kind of approaches, all possible approaches we knew, actually. And this is the same for carbon over phi. You see a quite flat behavior in the inner part of the galaxy, and then you see some dropping down in the outer part. This galaxy, amazingly, has an alpha over iron as high as 0.4 out to half of the effective radius, which is also consistent to the age to the old stellar population we find in the system. Okay, so not much of a gradient in alpha over phi and carbon over phi, and also a quite constant ratio among the two elements. So this is one of the main plot of this work that I would like to discuss with you a bit more in detail. So this is a plot in Italia 2, which is an IMF sensitive feature in the optical, let's say, and combining this feature with a TIO, another TIO feature, but in the near infrared, around 9,000 angstrom. Okay, so the amazing property of this plot is that this feature is essentially sensitive to abundance ratios, mainly alpha over phi and carbon over phi. That's why I was plotting them before. So it's increasing with alpha over phi, and it's slightly decreasing with carbon over phi, at least according to Corroy and Malocco models predictions. And it is also sensitive to the IMF, going from Krupa is 1, let's say, and then a more bottom-heavy IMF is here, which is quite, a big variation. So if we go to the near-infrared TIO feature, which is in here, you can see that this feature is even more sensitive to abundance ratios. Actually, it's extremely sensitive to abundance ratios. The effect is almost vertical in this diagram, but it is essentially not sensitive at all to the IMF. You see that the shift is almost horizontal in the diagram. Then you go to your data, which are here. This is the inner part of the galaxy. This is the outer part. And you see amazingly that there is a gradient in the along the horizontal axis. So as far as I know, this is the cleanest evidence that the IMF is varying radially. Besides, what you get when combining these different features as we did in natural work. Okay, so you can go farther. I mean, this is be more quantitative, so you can combine different optical indicators, and this is the way you fit them simultaneously with the chi-square approach, as you can see here. These are all the indicators that you have to be fitted, that we have been fitted simultaneously in the optical, from TIO2 to magnesium 47-8. And the black are the data points, the red curves are the best fitting models, so you get a fairly nice agreement when comparing to your model predictions. And this is what you get again, as you were expecting from the TIO2 plot. So you get an IMF variation, which is in red here from the optical indicators only, that goes, let's say, from bottom heavy to Krupa-like in the outer part of the galaxy. Okay, this is for bimodal, this is for unimodal. And this is, the red curves are just using the optical indicators as essentially we did for the Sloan analysis, okay? Well, but now you have much more. You have the XSHOOTER data, so you can also study the wings for Ben, which is at 1 micron. And the nice property of this feature is that this is really sensitive to very, very low mass stars in the IMF. So, and this surprise comes. This is the wings for Ben, and this is an optical iron indicator. So these are the predictions from Koroyan-Bandoko models. This is a Chabris, let's say, Milky Way-like IMF. This is a bottom-heavy model, which is much higher along the wings for band axis. Our galaxy is here. So the IMF slope is pretty much consistent if you just look at the plot blindly, let's say, with a Chabris-like prediction. Okay, so at the beginning you can be very worried about it, just looking at the plot, but then maybe, if you analyze things more in detail, you realize that there is something much more than this. So the dotted lines here, the dotted line here is the model prediction for a varying IMF. We did extended Miles models done by Alejandro Beni, who is there, using the IRT, combining the IRTF library with the Miles one. So as you can see, first of all, you can see that the variation for a bottom-heavy IMF, the variation that you expect from these extended models is about half of what you get from Koroyan-Bandoko models. But more important is when you compare the expectation for a unimodal model, which is, let's say, this segment here, with what you have for a bimodal model. The bimodal model is about half of the unimodal model prediction, and it's getting very, very close to the Chabris-like prediction. On top of that, you have the effect of alpha over iron, which is essentially moving the feature along in the opposite sides and along this axis with respect to the IMF variation. So you can fit the wing for band essentially using a bimodal and unimodal model, and then you compare to the constraints from your optical features. And the wing for band constraints are shown in blue here. This is for unimodal. Of course, you get something which is only barely, let's say, bottom heavy, which is, let's say, salpeter. So it's inconsistent with what you get from the optical indicators at more than 3 sigma. But for a bimodal model, for the reason that I was mentioning you here, you get very consistent result with what you get from the optical indicators. So the conclusion is essentially that in order to reconcile what you get from the optical with the wing for band, you need a tapering of the IMF at a very low mass. So you cannot have a unimodal model. This is excluded based on your spectroscopic constraints, and you have some kind of tapering. As I was saying at the beginning, it doesn't mean that the IMF has to be bimodal in shape, but you have to have a tapering at very low mass. So, okay, and this is one of the main conclusions, I think, of this XSHOOTER work so far. So you can put your IMF slope predictions in terms of mass to light ratios, and you can plot the so-called mass excess parameter alpha as a function of galactocentric distance in this galaxy. So this is the local property. So this is mass to light ratio normalized to the Krupa-like expectation, let's say. So for a bottom head, so Krupa-like is a 1 by construction, okay? And this is in the very center of the galaxy. Then because of the IMF gradient, it drops down to the Krupa-like value at, let's say, above 0.5 effective radii, or even before than that. This is the integrated one if you assume circular symmetry in this galaxy, which is pretty much the case. So you can integrate your stellar mass to light prediction over circular apertures, so mimicking somehow what you have, for instance, in Sloan. And this is the effect. You also have a gradient, but it is sort of shallower, of course, because of the average within the circles. So, and we went further, since we have also very nice kinematics for this galaxy, of course. We also computed the GEM modeling mass to light ratio. This was done by Michele Cappellari, essentially in the same way as he did, or at least as similar as possible to what he did for the Atlas 3D simple. And you can see that the dynamical estimate is here, and should be compared with this point here at same radius from the stellar population analysis in the galaxy. So you're essentially comparing, let's say, the total mass dynamical estimate with the estimate of the stellar mass from your stellar population study. As it has to be, actually, your dynamical model is giving a mass which is higher than what you get from the stellar population study. So this is very nice. So you are finding consistent results using different approaches, at least in terms of stellar mass to light ratio. And there is also some left space, which is essentially this size here, for some minor dark matter contribution within half of the effective radius, which is around 15%, something like this, and which is also consistent with other studies. So very nice consistency with the dynamical approach. So what I want to say here that using unimodal models and just sticking, let's say, with the optical indicators, you would easily get something which is, let's say here, in this kind of plot, which is inconsistent with the dynamical models. But I mean, the good thing here is that this kind of work, and this is the first time that spectroscopic indicators by themselves are ruling out, let's say, a single power law model. So you're really able to exclude that based on your spectroscopic features and not just comparing to other independent constraints. Okay. Now I want to, this is essentially the second last slide before summary of my talk. So this is, that there has been this recent issue in Smith et al. Papers about high velocity dispersion galaxies with a sort of light IMF. Which means that the stellar mass, let's say, of these galaxies, of at least these three galaxies, three naughty guys you see here, which is too low with respect to what you would get for a bottom-heavy IMF at the same velocity dispersion, but it seems to be more similar to what you get for a Krupa-like IMF. So there has been a big discussion about why, these galaxies are like this. So this is, for instance, the trend. The filled circles are galaxies from Corolla-Mandokon 2012, plotted as a function of velocity dispersion and magnesium over iron. Here, you're not plotting the IMF slope, but the max excess parameter. So we are talking essentially about stellar mass to light ratios, okay? So, and the yellow area here is the one that Michele and collaborators got for the Atlas 3D sample that stops around here. So it's quite clear that these galaxies, I think you should focus more on the blue points, because they account for the realistic age constraint that you can get from the spectroscopy, and with also including some, effect of realistic effect for dark matter in the galaxy centers. So as you can see that admittedly these galaxies seem to have lower mass to light ratio with respect to the most of the points that you have here. So of course, I mean, something that we should keep in mind that you really miss, a complete sampling of this region. This can be also, this is probably more clear here. In this region, in terms of magnesium over iron, you essentially have only 1 point. So this is something that we have to keep in mind. So, and of course, you can ask yourself where our XSHOOTER galaxy is. And there, where we go. So in here, I'm plotting the center, I'm going from the central region of the galaxy outwards. Okay, out to one effective radius in both plots, and essentially the pink area that you can see is the range, the 1 sigma uncertainty on the mass excess parameter that you have from your spectroscopic analysis. So the nice thing, for instance, if you look at well, first of all, you have to realize that the aperture effect because of the IMF gradient is a very important one. You can see it in here. You essentially go from something which is 2 to essentially something which is 1.4. Okay, so if you take spectra above the spectra of our galaxy outside half of the effective radius, it is consistent at the 1 sigma with the Russell with Smith et al. Lenses, at least for 2 of them. Although these 2 galaxies have a higher sigma, than our galaxy. Well, this is certainly not a conclusion, of the story, but it clearly shows that we should keep IMF gradient seriously into account, and we need a proper sampling, let's say, of the high mass and of the distribution for this kind of analysis. Okay, so this is my summary. So just to give you some take-home messages, about this story so far. So we have detected a clear, very robust IMF slope sigma trend from the Sloan data. As I was showing you, the optical indicators do not allow us to really point down, let's say, the shape of the IMF, and this implies a large uncertainty in the stellar mass to light ratio. So be very careful about this. So the trend seems to be mostly due to a local correlation with the metallicity rather than magnesium over iron. So we have detected a clear IMF radial gradients in early type galaxies in the sense that the dwarf enhanced population is really in the core region of the galaxies. So a bottom-heavy IMF requires also that we start thinking about the time-dependent scenario and the consequences of that, which are important for our understanding of galaxy evolution in general. We are finally able, using our XSHOOTER data, to rule out a unimodal distribution, which also helps in the comparison to independent constraints from dynamics and lensing. And some of the things that we're doing here, and then maybe I will talk about this next time, is enlarging our XSHOOTER sample and also looking with the same technique at dwarf spheroidal galaxies. So thank you very much for the attention. Okay, I can leave this one.
Have you tried to do the same exercise with globular clusters where you can check individual stars? And because you know that there are these weird stellar populations there.
Yeah, so, well, this was the paper from Correa and Madocco in 2012 also addresses this specific issue comparing to two globular clusters in M31, which have similar abundance ratios as and metallicities as the massive galaxies that we're talking about. And they show that actually you don't detect this enhancement at least in two features, which are the sodium 8200 and Wingfour band. So you wouldn't infer, let's say, a bottom-heavy population for these two clusters, for these two globular clusters. What we will also look at that, by the time of the CALIFA paper, this CALIFA paper, we find a correlation of IMF slope with the metallicity, which comes from a correlation of this TIO2 indicator with the total metallicity. We were looking at the same kind of relation for the data of globular clusters which are available from Schiavone et al. 2007. And what we see is that there is a correlation with metallicity up to the point that the stellar population models actually predicted, which is subsolar metallicity, but then there is no correlation whatsoever, while early-type galaxies keep going up, which means that you would infer a bottom-heavy population only for the early-type systems, which is an important check indeed. Of course, eventually what you would really like to have, for instance, is something like this kind of XSHOOTER spectra for globular clusters of similar, if possible, chemical composition to your massive galaxies and make, a more extensive comparison. I think this is something very much needed. But, so far, that's the answer.
So, can you go back to the slides where you were exploring the difference in the IMF using optical features and near-infrared features? So I was wondering, that one. So I was wondering whether the data is now good enough to go beyond even the bimodal hypothesis and try to see which IMF shape would you, the global range you could have just to have a perfect matching. So,
well, this kind of work something that I didn't say maybe, we are still relying on the dependence of this feature on alpha over iron from the theoretical Conroy and Madocco models. So in a sense, we have to trust this kind of prediction. So of course, the data are good enough that you can in principle go beyond, let's say, you can constrain, in principle you could constrain the IMF shape as well as you want, because you have so many indicators. But the problem is that these kind of predictions also bring some uncertainty, which is very difficult to quantify. So my answer to your question is that I think this will be probably feasible, but we really need to observe a range of galaxies with different abundance ratios in order to also quantify the uncertainties on the abundance corrections. This is what is hampering, at the moment, the constraints that we can put on the IMF shape.
My question is, early-type galaxies, some of them are byproduct of weight process, gas-rich process, where on the other hand, you have most massive ones, which are thought to be a product of dry merger. Have you looked at if there is any trend between these formation scenarios and the IMF?
Yeah. Well, as I was mentioning at the end, Yeah, I think this is one crucial point, actually. So I think in order to address this issue properly, and we really have to do it, actually, we would need a good sampling of this region in this diagram in order to really, observe galaxies with different properties. For instance, and this follows what you're saying, galaxies in this regime, they have a variety of metallicity gradients, and they probably result from different formation channels, as you are mentioning. So it would be very nice, to connect this, to the IMF gradient that you have in the galaxies, in order to see if there is some kind of connection with the formation channel, actually, as we may think. But we really need, to have, a good sampling of this region, which is what we are trying to do.
Exactly. What is also true is the Faber-Jackson relation is thought to saturate. So you have L, which is almost independent of sigma at this extreme. For extreme massive galaxies, so probably there might be something going on at that end.
Yeah, no, I think this is really something we have to go after.
I have two questions. Maybe they are very stupid, but I am.
Maybe they are, sorry?
Maybe the questions are very stupid and very easy, but when you are doing all the analysis, you are talking about initial mass function, also about metallicity evolution. What is the star formation rate? Because you cannot have, if you have, there must be somewhere. I mean, if you have a single burst of star formation, there is no metallicity evolution in a star pair because there is no more formation of stars. So, and I assume that you are using some way all the time single stellar population models. So, well, it is the first question, and the other, when you are talking also about initial mass function variation along the radius, somehow the stars that have been formed must move dynamically inside the galaxy. So, well, I don't know the galaxy dynamics, but you can assure that in a given radius, all the stars you have there has been formed at the same time, so you can talk about an initial mass function there, or if there is a mixing of star formation histories along the galaxies, there is also a mixing of the resulting initial mass function.
Okay, so about the first question. So from the point of view of analyzing the data, we have played also with the models having different star formation histories, okay? So we have considered one SSP models, but also more extended star formation histories. And when comparing, let's say, model predictions to data, we always get, the sort of very similar IMF trend. So, and this mostly happens because we are considering massive galaxies which had very old population, and they formed the stars in a relatively short interval of time. So adopting more extended star formation histories doesn't really make much of a difference. If you are concerned about the toy models, let's say that we were playing with, in our work with the Karsten and also with Ignacio Ferreras, those are very simple, chemical-rich and toy models, closed box models, where the star formation history was something like a Gaussian or something like this. And essentially you get something, the star formation time scale is actually constrained from the observation. So you have a short but still extended star formation history with a time scale around 1 giga-year. And this is the time scale where you should switch, let's say, from a top-heavy to a bottom-heavy phase in order to recover the different
Okay, and in general, a time scale for 1 giga-year allows to put galaxies, elliptical galaxies, from potentially zero metallicity at the origin to twice solar metallicity. Only
yeah, the first phase,
year.
which is the top-heavy phase, is where you produce, let's say, the most massive stars like crazy, and then you reach the medium enough to get the metallicity you want to get.
Okay.
But then the second part is essentially the bottom-heavy phase, which is dominating at low mass, and then it brings the IMF sensitivity constraints that you get from the spectra.
Okay.
So. This is about the mass segregation that you are mentioning about. Well, I think the system that you are talking about is something for which, as far as I understand, mass segregation is not important because of the size of the system itself. We're talking about a typical size of 10 kiloparsec. something that is radius. So with a velocity dispersion which is typically 300 km per second. So you cannot have, let's say, massive segregation of a massive outflow, for instance, of stars from the very core to the other part of the galaxy just because of that. I think. Yeah. With compare, for instance, to a globular cluster,
Hi, have you considered using the calcium triplet and metallicity relation for the Muse data, for example, because it has a high resolution for red giants in the globular clusters?
Yes, I have considered. Actually, this is what we are doing for the dwarf galaxies with Jacomans and Reine Pelletier. But I have to say that the main issue in that case is that you miss the calcium abundant indicators, like for instance the calcium 4227 feature. So this hampers, the estimate of calcium abundance, and as a consequence, the use of the calcium triplet indicator as an IMF indicator.
More questions? No? So before we go to the coffee, let's thank Francesco again for